All right, here we are in our lesson of putting it all together. We did it! Unit 3! Woo! All right, you know how to take the first and second derivatives of functions. You know how to apply the first derivative test of extrema, right? So we're going to use the increasing to decreasing, decreasing to increasing number line. You know how to use the first derivative to determine those intervals of increasing and decreasing. We know how to use the first derivative to determine where a function is concave up. That would be f prime increasing, or concave down. That would be f prime decreasing, right? First derivative, f prime. We know how to apply the second derivative test of extrema. So we would take f double prime of some critical number and determine if our graph was smiling or frowning, creating a minimum or a maximum. We know how to determine if a function has an inflection point. From the graph of a first derivative, we would see extrema. From the second derivative, we would see a root, changing from positive to negative or negative to positive. We know how to use the extreme value theorem. Absolute max and min has to be on a closed interval from a to b, and we set up our candidates test with a and b and all of our critical numbers in between. We can apply the mean value theorem, which says that if f is continuous and differentiable on the closed interval and the open interval respectively, then f prime of c equals old school slope, I rock equals a rock. Rolle's theorem adds the extra condition that f of b is equal to f of a in addition to being continuous, and differentiable, means that f prime of c will be equal specifically to 0. The connection between Rolle's theorem and mean value theorem is that because f of b and f of a are equal to each other in Rolle's theorem, this numerator just turns into a big fat 0, thus the connection. Be able to evaluate and apply infinite limits. So to infinity and beyond, do you approach 0? Do you approach the leading coefficient over the leading coefficient? Or do you approach, well, technically DNE, but then describe it? If x is going to plus or minus infinity, what is y doing? Is y going to plus or minus infinity depending on your division? I don't know why I switched colors, but I did. Be able to use the first derivative, second derivative, and infinite limits to be able to sketch a curve of, I cut off the bottom of this slide, but okay, that's what we're going to do today, putting it all together. All right, so when we talk about putting it all together with your analysis, the first thing we want to talk about are all the things that we remember from pre-calculus. Woo! So you want to check if there's any discontinuities, which is the same thing as finding the domain, which is checking for any place that we divide by 0, whether that be a whole or a vertical asymptote, right? Whether it's a removable discontinuity or a non-removable. And then if we're talking about a piecewise function, we haven't seen those in a little while, piecewise function, we'd want to check the 3 pillars and make sure that we didn't have a whole, a vertical asymptote, or a jump, right? No discontinuities. Are there horizontal asymptotes? What is the end behavior? So this is when we talk about top heavy. We're going to go to plus or minus infinity because there is no horizontal asymptote. Even heavy, we're going to go to leading coefficient over leading coefficient, which is our horizontal asymptote. And what did I miss? Top heavy, even heavy, bottom heavy. That's what I'm missing. Bottom heavy, the limit will be 0 because our horizontal asymptote is 0. So remember, end behavior is the same thing as finding the limit as x approaches infinity. That would be going out to the right. Or the limit as x approaches negative infinity, which would be figuring out what is the end behavior to the left. What is the y-intercept? Good old find me f of 0. Okay, so we're looking for a point 0, comma, something. If possible, what are the x-intercepts? So we're going to set our original function, the OG, equal to 0, just like we've done most of our lives in math class. So I'd be looking for possible places where my original function crosses the x-axis. All right, so that was a pre-calc review. Let's talk about the calculus. That's the exciting part, right? So find the first derivative, f prime of x. In doing this, you might need a product rule, a quotient rule, a chain rule, some trig derivatives, whatever it might be, in order to get that derivative. Then you want to find the critical numbers by setting f prime of x equal to 0, or considering where f prime of x is undefined. I'm going to skip to part C, determining increasing, that was supposed to be green, increasing and decreasing intervals. We do that by taking our number line, labeling that number line f prime of x, so we know what we're referencing, plotting some critical numbers, whether they came from 0 or undefined, and then doing some test situations. So intervals of increasing or decreasing, positive or negative. Then, based on what we have, we can find the y values of those critical numbers, and those will end up creating our extreme values. Remember, if we're on a closed interval, we also need to test our endpoints, so A and B, and then we would put those critical numbers from inside the interval into there to be able to figure out our absolutes. But the other ones can be relatives based on if f prime is changing from positive to negative. This would represent a relative max. This one actually represents, sadly, nothing, right? Just a brief horizontal tangent in that case. What else? Oh, the extreme values. Remember, those are the outputs, the y. So the critical numbers is where those things occur. That's like listing the name of the student. The extreme value themselves is like naming the height of the student. All right, so then we can use the second derivative, f double prime of x, to find our points of inflection. Well, finding points of inflection, we're going to consider where would f double prime of x be equal to 0, or where might f double prime of x be undefined. Based on that, we will set up a number line, this time named as f double prime of x. We can plot those critical numbers. That was supposed to be purple. Come on, pen, work with me. Plot those critical numbers, whatever they might be. Do some interval testing to see if things are concave up or concave down based on the sign of f double prime. Then we can put it all together to graph our information. These are most of the factors that go into making that graph. So again, remember that your original function, f of x, can be increasing, decreasing, concave up, or concave down, which means that f prime of x, if f is increasing, f prime is positive. If f is decreasing, f prime is negative. So above the x-axis or below the x-axis. If f is concave up, f prime is increasing. If f is concave down, f prime is decreasing. Thinking about that then in the next layer, this we don't have any information. Okay, that's not helpful to us. But in this layer, if f prime was increasing, then f double prime is positive. If f prime is decreasing, then f double prime is negative. So our four ways that we have our curvature, which one am I missing? Oh, this one. All right, so in this case, we are increasing, but we are concave down. Here we are, no, I drew that same one twice. Come on, Schwartz. This is what I'm missing. This, but that's the wrong color. Oh, come on. Like this, increasing, but concave up. This one is decreasing, concave up. This one is decreasing, concave down. So these four curvatures are the four combinations of increasing while concave up, increasing while concave down, decreasing while concave up, decreasing while concave down. All right, so four different curvatures that you need to be aware of. Remember that points of inflection happen on the original when we change concavity. You can see those in the extrema on f prime, or you can see those in the roots of f double prime, right, where these things change back and forth. Likewise, increasing to decreasing, this is an extrema on the original, which means we will see a root crossing the x-axis on f prime. Think about what happens in between those intervals, right? Where those critical numbers might be. Reminder two, the last chart that we've looked at, putting together those four curvatures could look like this. This would be a critical number where f prime is equal to 0. This would also be a critical number where f prime is equal to 0. On this one, if this black curve represents f, so the black curve is f of x, then here f prime is positive because f is increasing. Here f prime is positive because f is increasing. Here f prime is negative because f is decreasing. Here f prime is negative because f is decreasing. This whole part put together, the second derivative would be negative, f prime would be decreasing. Any part of this curvature, f double prime would be positive, and f prime would be increasing. Again, that's just following from this chart. If f was concave up, f double prime is positive and f is increasing. If f is concave down, then f double prime is negative, which means f prime was decreasing. What this does for us is it shows us that critical numbers come from when f prime is 0, or where f prime is undefined. But when we have the ones that are equal to 0, we can test to find a max by either using the first derivative, changing from positive to negative. Or we could test using the second derivative, taking that critical number and just figuring out, is f double prime of that critical number negative? If it is, then we have found a maximum. Or, in the case of the bottom, if we do f double prime of that critical number and we come back with f double prime positive, then we have found a minimum. High point when we're frowning, low point when we're smiling. I would say that's the only one that kind of goes against your gut, right? All of these other words, concave down, frown, f prime decreasing, f double prime negative, right? It's all very like downer language. But if f is concave up, f prime is increasing, f double prime is positive, we've got big smiles on our face. I know, it's a little overdone, but it's 8 o'clock at night and I'm recording this video. So, these are your two summary charts that I think are most important for this unit. Again, the full analysis is how you would put it all together, but it's really understanding about how each layer is synonymous with something else. So if you are given a problem that says, hey, you know what, f prime was increasing. What does that show us? That shows us f was concave up, and it shows us f double prime was positive. Hey, I'm telling you f of x was decreasing. Cool, I know that f prime is positive. All right, so those things need to start becoming like translations for you in your head, okay? Synonyms. We have to know this information so that when we see it written down or we see it in a graph, whatever is provided to us, we are able to navigate through it. All right, that's putting it all together. A full summary of Unit 3. Please rewatch this video or rewatch any individual videos about that full list of topics that you feel you might need a refresher on.